All right, so where were we last time? So we had derived the fermion Lagrangian, which is at the top of the board. And really the only difference between this and what we talked about earlier is that we had performed the multipole expansion. So we distinguished between collinear momenta that are scaling like a collinear momentum and momentum that are scaling like an ultrasoft. And only the collinear pieces were showing up in here. And same with the collinear gauge field. It was only showing up in here, whereas both were showing up in here. There's only a single type of derivative here because ultrasoft and collinear momenta are the same size in the n component. But they're different in these other components, so we had these labels and this label operator that picked out the collinear momenta, so we could define collinear covariant derivatives, if you like, with this subscript n, whereas this d is kind of like a full derivative that involves both types of gauge field. And then at the end of lecture, it was kind of rushed, but I was talking about the collinear gluon Lagrangian, and I said there was a set of replacement rules that we could make to effectively do the same thing that we did here. And now I've just written out for you what that Lagrangian is with those replacement rules. So curly D is basically just taking all the derivatives and taking only the leading order pieces. So we take the collinear pieces in this component and this component. We take the ultrasoft pieces in this component. And then if you wrote the original Lagrangian as a commutator of two covariant derivatives, you just replace it by the leading order pieces. And that's what the leading order action will be. Then we had to think about gauge fixing. Since this is the collinear gluon Lagrangian, we should think about collinear gauge fixing. This here is a general covariant gauge fixing with parameter tau, and then there's a corresponding ghost term. And in this Lagrangian, the usual way it would look, this would be I partial. And then I said that because we don't want the collinear gauge fixing term to break ultrasoft gauge invariance, we're going to turn that I partial into a covariant derivative we're going to include this piece here at the n.a ultrasoft to make it collinear, to make it ultrasoft gauge invariant at lowest order. Okay, so that's really the only other than just doing this sort of most naive thing by just replacing derivatives by covariant derivatives. And you might think, well, I'll just keep this as a partial derivative since it's doing gauge fixing. I don't need to make it covariant. But we do want to make it covariant under the ultrasofts. And that's why I write this curly d ultrasoft. OK, so that gives you the leading order Lagrangian. Once you put together this with what you want for the ultrasoft, then you would have the full leading order Lagrangian. And the ultrasoft part is actually very simple. So for the ultrasoft part, we just take a full QCD action for the ultrasoft field. So this is just psi ultrasoft, or Q ultrasoft bar ID slash ultrasoft Q ultrasoft. And likewise for the gluon piece, it's just QCD. And we would do the gauge fixing without thinking about any complications like these ones. And these are just involving ultrasoft fields. So just QCD, just ultrasoft fields. OK, so the only place, when you take everything here together, the only place that the ultrasoft and collinear fields talk to each other in the Lagrangian is in this single component, n.partial, n.a, ultrasoft. And that comes about basically because of the power counting, that this is really the only place that these two things can interact. And we'll talk about the implications of that later on. OK, but that's the leading order Lagrangian. So once you have this piece, then this piece is pretty straightforward with this additional complication of worrying about what gauge symmetry means, which we'll talk more about later. But we had to be careful not to break it when we introduce this term, because we want to, in some sense, have a gauge fixing both for the collinear gluon and a separate gauge fixing for the ultrasoft gluon. And that's why we wanted to do this. And then this piece here is simple. It's just QCD because it's, if you like, it's the lowest energy mode. And it doesn't know about any of the complications that we had for the collinear modes. OK? So any questions about this so far? OK, so everything that we did in deriving these actions is tree level. All the steps that we did we're tree level. So you can ask, if I start to do loops, will there be some Wilson coefficient that shows up somewhere here? Will I generate some new operators that I don't see here? Those are reasonable questions, and that's what we're going to address next. So to go further, we'll use symmetries. And we're actually going to consider 3 different symmetries. Gauge symmetry, which I've been promising you for a while. Reparametrization invariance. And spin symmetry. Or I'll put a question mark by this last one because we need to answer the question whether there even is a spin symmetry. These two here, this number 1 and number 2, will turn out to be quite important. Number 3 is not so important. So reparametrization invariance here will be like reparametrization invariance in HQET, except now it's different. We've introduced the parameters n and n bar. And we'll have to see what kind of symmetries we have with those with respect to that choice of basis vectors that we made. But it otherwise will be analogous to our discussion of HQET. So let's actually first dispense with the one that in some sense is the least important, this number 3. So first, let's revisit our spinners a little bit. So if I put together the information that we talked about when we derived the equation at the top of the board there for the Lagrangian, we worked out that at tree level, we have this formula that relates the fields. So from that formula, if we just project onto the spinner pieces, we can write down a formula that relates the spinners. So throwing away the gauge fields, we have in momentum space that u of p, the spinner, would be related to whatever spinner we have for this Cn field, which I call un, by that formula. And then if you take this formula, you also see that if I hit it with a projector, n slash n bar slash over 4, if I hit the u with a projector, it's going to kill this piece because the n slash n bar slash can be pushed through the p perp slash, and then n bar squared is 0. So that kills that second piece. So we also have this formula. And then once you have this formula, you have the formulas that we kind of wanted for that. Okay, but this spinner here, this un, is not exactly the same as the spinner that we talked about earlier. So let me come to that in a minute. So first thing you might consider is whether when I take this Cn field and I take the Lagrangian up at the top of the board, do I just get the linear propagator that we talked about? And indeed you do. So if you consider, it's kind of obvious for the momentum-dependent parts, and really you might only worry about the spin. And so if you consider this formula and you consider the sum over spins of u bar, which is what's going to appear in the numerator of the propagator for the fermion. When you're deriving the fermion propagator, you get a sum over the physical spins. Then from this formula, this is a projector on something you know how to do the spin sum for, which is the full theory spinner. And that spin sum is just p slash So this is like P slash sandwiched between projectors. And you can work out that that's exactly the numerator that we had before after a little bit of Dirac algebra. So that part works as expected. If we take this Lagrangian and we work out what the propagator is, we get exactly the propagator we got from expansion. So quantizing LC0 gives us that propagator. But the situation is not quite the same for the spinner. And in some sense, this is not, this point is not absolutely crucial, but actually, because there's a little simplification I want to do in order to discuss the spin symmetry. And in order to do that, at this point, it's important to understand this point. So that I'm going through this in some sense because then it'll be very easy to discuss what spin symmetry we have in the theory. So this guy is actually not equal to our expanded spinner, which, putting in some normalization, I could write like this. So this is what we got by expanding. Something like this, which is very simple, where this u was equal to 1, 0, or 0, 1 in the Dirac representation. But that's actually not what we get if we just take the formula up here and use this. So let's see what we do get. So if you use the formula up there, then you have the following. So here's the full theory spinner with sort of a conventional normalization. So this thing, and this thing here is the projector. Okay? So you could work out what that product is. And it turns out that you can write it in the following way, which is very closely related, but not precisely the same as what we had before. So you can write it in what looks like the same form as we have over here, except this curly U, curly capital U, is a more complicated object. And it's just whatever I get by multiplying these two things out, which turns out to be something I can write in that form. So it's some two-component spinner, but it's got momentum dependence, unlike our simple 1, 0 and 0, 1. But everything we said about UN really depended only on the fact that it could be written in this form in terms of some two-component spinner. The fact that n slash on it was 0, the fact that it had a projection relation. So these formulas here, once you have, you know, if you have a formula like these formulas here are true. Okay? So actually, it would be true whatever spinner we have there. So why should I want this U twiddle spinner rather than the U spinner? That actually has to do with this reparametrization invariance, so it'll become clear when we talk about that. But these extra terms in U, relative to those for the other guy, the simple U, actually ensure the proper structure under reparametrizations. And basically, it'll become clear in a moment, but basically, if we wanted to get this U spinner, we should have a slightly different projector. Which I'll call Pn prime. And it's so we could have used a different projector, which is this one. And then we could have come up with another projector, which was the Pn bar projector, which would satisfy that the sum is 1. If we wanted. And this projector here, when acting on the full theory spinner, would have, the full theory field would have given something that would have been proportional to this combination over here. Okay, so you just have to believe me. I don't want to go through the algebra, or you can check it yourself. But this projector here is not invariant under that symmetry of reparametrization invariance. So when we talk about RPI, it'll be clear why we want a projector which is this projector and not the slightly different projector, which is this extra, has this extra n//2. OK, but nevertheless, the important point that I wanted to emphasize is really that we have this kind of way of decomposing the spinner, the true spinner for our field Cn, in terms of a two-component object, U twiddle. OK, so this is, we are able to do that. And if you want to talk about spin symmetry of the theory, it's easier if you use a two-component notation. So the reason that I wanted to go through this is really to have on the board this equation, which I can then use to motivate writing down a two-component version of Cn. And once I have a two-component version of SCET, then it's very easy to see what the spin symmetry is. So let's write down this two-component version of our linear quark Lagrangian. You can do the same thing, of course, in HQET. You write down a two-component version rather than a four-component version. If you have a four-component version, it has this projection relation. If you have the two-component version, the projection relation is built in. The reason to consider the four-component version is if you want to couple this object to four-component fields, like the ultrasoft field, then it's, of course, a nice thing to have a four-component version. But some things are easier in two components. So take Cn and write it as follows, with this phi n as two components. And I've set things up so the dimensions of Cn are equal to the dimensions of phi n. OK, so I can take that formula, plug it into our SCET Lagrangian, and then I can, using the Dirac representation for the gamma matrices, write out a Lagrangian for this phi n. So that requires doing a bit of algebra, which I will take you through. And then we get an equivalent Lagrangian, but in terms of this field, and it looks as follows. Okay, so it's almost independent of spin, but not quite. There's this sigma 3 sitting there. If sigma 3 wasn't there, it'd be like HQT, where you'd have an SU2 symmetry. The fact that sigma 3 is there means you don't have an SU2 symmetry. And really all you have is a U1 symmetry. And that U1 really corresponds just to helicity. So in 4-component notation, that U1 would be following. It's projecting the spin operator onto perpendicular indices, antisymmetric in both of them. And in the 2-component, that just becomes a sigma 3. So obviously, if we do an exponential rotation with respect to sigma 3 commutes with sigma 3, so does the identity. And so we could have a rotation of this guy by that. And that's the only spin symmetry that you have, is this helicity. And so because of the coordinates we're using, this corresponds to the spin along the direction of motion, which is the 3 direction, if you like. Which sometimes we denote by just saying it's along the direction n, which is then more independent of how we pick our axes. So this symmetry here is actually related to what you would call the chirality in QCD. So it's not really a new symmetry. So this is just related to the chiral rotation. So if you look at gamma 5 times c, then gamma 5 in our representation would be 0, 1, 1, 0. And then if I write it out in terms of this 2-component thing, then that is just giving me 1 over root 2. And it's swapping up and down. And so that just means that phi n has gone to sigma 3 phi n. So multiplying by gamma 5 is actually the same as multiplying by sigma 3 in the 2-component notation. Okay, so this is not really a new symmetry. And actually, all the usual things that you would say about chiral rotations in QCD would apply here too. So chiral rotations, of course, are not exact. Chiral rotations are broken by masses. Chiral rotations are broken by non-perturbative effects. You can worry about anomalies. They are useful in perturbation theory for quantifying operators, and that remains true here. But if the collinear fields were non-perturbative, then you should worry about those other things as well. Okay, so spin symmetry, there's not really anything new there to talk about. But along the way, we saw we could write SCET in 2-component form, which is kind of nice. So let's talk about something that's more important, which is gauge symmetry. Is there any questions about the spins before we talk about gauge symmetry?
So is the extra term you got from integrating out the zeta n bar, that is why you had the minus n slash n new projectors and why you don't have the full SU2 and stuff like that?
Yeah. I looked at it once, but it's hard for me to remember the answer. I think not, but I think if you do the other version, then you just get something more complicated here, but still breaks SU2. Like,
Okay.
Yeah.
Okay, okay, I'm just looking for some
Yeah.
intuition.
So they're two disconnected facts. The thing that, that I wanted to motivate that I could use this formula, and I wanted to be honest with you about where that came from, and that's why I told you this other fact. But I could have jumped right here and said, remember, and glossed over it, and that would have been fine for this discussion. So they're in some sense two disconnected things, at least in my mind. Yeah.
Do you have some intuition for what theta n bar is?
For theta n bar.
Yeah, is it the thing
See,
you're going to
yeah, I mean, it's really just saying, my intuition for it is really just that when you're producing energetic particles, you know, it's what we did at the beginning. Right? When you're producing energetic particles, these are the spin components that you have at lowest order, and that leads to, if you like, that the fact that you have this form and you have this projection relation is kind of non-trivial, even though you don't have a spin symmetry. I mean, there is something to it. It's not like a SU2 symmetry of the spin, but it does, for example, when you go and look at form factors, it does lead to non-trivial relations for those form factors. So I don't call it a symmetry. I don't think of it as a symmetry, but because it's not a formal group theory statement of Lagrangian, but